In today's lecture, we are going to talk about the impact of climate change on monsoons. And all of you realize that this is a very important issue because India is a country with 1.4 billion people and our agriculture depends on the monsoon rainfall from June to September primarily. Okay? And already in the last 75 years, our population has gone up more than 4 times. Okay? So, the per capita availability of water has already gone down by a factor of 4. So, on account of climate change, if the monsoon rainfall decreases, then we as a country will be in serious trouble. So, it is important to understand what are the consequences of climate change on monsoon. This is a difficult topic because monsoon is a complex system, okay, which is influenced by the sea surface temperature around India, Arabian Sea, Bay of Bengal and Southern Indian Ocean, as well as what is happening in the Atlantic Ocean and the Pacific Ocean. Okay. So, year to year monsoon rainfall keeps changing and our understanding of monsoon has improved a lot in the last 60 years on account of lots of observation and satellite data, but still our ability to predict how monsoon will change on account of human induced changes like carbon dioxide increase and aerosol is not that completely understood. Okay. So, before I go into climate change, I want to clarify some issues about monsoon itself. Okay. Monsoon is influenced by greenhouse gas warming definitely and influenced by changes in circulation of atmosphere called dynamics, has a strong dependence on thermodynamics, temperature, humidity and so on, and depends on how the land use is changing the surface albedo of the earth, and of course, there is the impact of aerosols. So, all these are having an impact on monsoons and the net effect can be complicated because some of them increase, some of them decrease and the net effect may be one way or the other. Okay. Now, here is a simulation of rainfall, daily rainfall over India in the year 2021 and you can see it is not regular. It fluctuates from day to day and systems are coming from Bay of Bengal, from equatorial Indian Ocean, from Arabian Sea. It is a very complex system. Okay. So, the short term forecast of rainfall now is quite good based on weather forecast models, but here our main focus will be not on the short term forecast, but on long term prediction. What will happen next year or after 10 years or after 50 years, that is the issue we are going to talk about. Now, I have to first make sure that some of the things you learned in the schools have to be changed now, because normally in many textbooks they say monsoon is like a giant land sea breeze driven by contrast between a hot continent and a cool ocean. This was an idea proposed almost 300 years ago. Okay. But this is wrong and you will see why it is wrong. This is okay to understand coastal circulation. If you are in a coastal region, in the afternoon the land heats up, air becomes lighter, it rises and cool moist air comes from the ocean and we have a circulation. This is a local circulation which extends to the height of maybe 1 or 2 kilometers, that is all. Okay. This is called the land sea breeze. All of you who have lived in coastal areas have experienced this, but this is not monsoon. Okay. Monsoon is a much bigger system. As I said, it is influenced by Pacific Ocean, Atlantic Ocean and so on. So, it is not a local land sea breeze. Now, why is the land sea contrast theory not valid? I am talking about contrast in surface temperature. Okay. Because after the monsoon starts over India, the monsoon onset around June, the difference in temperature between land and ocean becomes very small. Land becomes cooler by around 10 degrees, and then you do not see much change between land and ocean. Okay? And you look at a place like Sahara in Africa, where there is no rain, it is very hot. The contrast between Sahara and the surrounding Arabian Sea and Atlantic Ocean is very large, but there is no rainfall there. So, land sea contrast being high does not guarantee rainfall. Okay? And in India, in years when there is very good monsoon, rainfall much above normal, the temperature difference between land and ocean is smaller because land cools more. Okay? And in years when monsoon rainfall is small, there is a drought, the land sea contrast is higher. So, obviously, the land sea contrast that we see during the monsoon is a consequence of rainfall, not a cause. So, the cause and the consequence should not be misunderstood. Land sea contrast depends on rainfall. So, in a good rainfall year, the land sea contrast is small. In a poor rainfall year, land sea contrast is large. So, land sea contrast temperature is caused by monsoon rainfall, is not one which causes monsoon rainfall. Okay? So, there is no relationship between surface temperature of land over India and that of the ocean surrounding India and its rainfall. Okay? That can be shown clearly. Look at the July surface temperature average over 50 years between 49 and 2002. You see that land is slightly colder than the surrounding ocean. Okay? So, land is not hotter than the ocean in July after the onset. Okay? Now, if you look at the vertical structure, which is very important for monsoon, you see a big difference between July and May. In May, land is hot and there was a land sea breeze, especially in South India, and that causes an upward motion. That upward motion is there only up to a height of over 2 kilometers. That is not monsoon. That is local circulation driven by land sea contrast. But in July, the vertical motion extends up to 5 to 6 kilometers, and that is the real monsoon circulation. This is a local circulation in May, and in July we have monsoon circulation. You see the difference in the kind of clouds we have. We have deep clouds during the monsoon, and before monsoon you have shallow clouds which go up to 2 or 3 kilometers. Now, if you look at the August rainfall in Asia, you see the highest rainfall is not over land, it is over the ocean, Bay of Bengal and West Pacific. Okay? So, quite clearly the circulation that drives the monsoon is not due to temperature difference between land and ocean, which is very small anyway, but the ocean is one which plays the important role. So, the best way this is explained by Clift and Plum in their book The Asian Monsoon is that the ocean stores the solar radiation because there is a thick mixed layer where ocean is well mixed up to about 50 meters or 100 meters thick. And what is important is the land sea contrast in heat storage. Land cannot store heat, ocean can store heat. That is what makes a big difference in the monsoon circulation. Okay? So, this difference is very important, but not surface temperature. Now, here is an animation of the temperature of the cloud top obtained from satellite called outgoing long wave radiation, you know that name. And you watch this from January, it is over Indonesia, and it gradually moves by May into Bay of Bengal, then comes over India in July, August, then goes back. Okay? So, the monsoon clouds move between Indonesia and India, that is southeast to northwest movement of the clouds. It is not north-south, it is moving from Indonesia towards India over the whole year. This is an annual cycle being shown here, and you can see that Indonesia is a place where the clouds are in January, and they move gradually by May into Bay of Bengal, then into India. They stay over India for some time, and then they go back to Bay of Bengal and back to Indonesia. The cycle repeats. So this shows that the temperature of Indian Ocean and West Pacific Ocean plays a very important role in the way these monsoon clouds move. Okay. Now, to get away from this land-sea contrast theory, which we know is wrong, a new approach has been proposed based on energy budget. This idea is that monsoon is a giant heat engine. Monsoon takes the heat stored in the ocean, and that heat stored in the ocean causes evaporation of water vapor, which comes over in the atmosphere, condenses there, and when it does so, it sets up circulation. Okay? So, monsoon is a heat engine which converts the solar energy stored in the ocean into the kinetic energy of the monsoon. Okay? Monsoon is a mechanism which converts the solar heat into kinetic energy by the condensation of water vapor in the atmosphere after it evaporates from the ocean. So, ocean is very important, sun is very important, not the land-sea contrast. So, monsoon is a heat engine, and all of you have heard about the heat engine idea in thermodynamics, the famous Carnot cycle, Carnot engine. So, monsoon is a Carnot engine which operates between the warm surface of the ocean and the cold atmosphere at the height of about 5 kilometers. So, the monsoon heat engine, the heat source is the surface of the ocean, and the heat sink, the condensation, is at the height of 5 kilometers, which is much colder than the ocean. Okay? Ocean may be at around 300 degrees Kelvin, while at the height of 5 kilometers, the temperature is more like 270 Kelvin, okay? Less than the freezing point of water. Now, to understand this concept of monsoon, you must look at satellite data. Only satellite data gave us the true idea of what the monsoon is. So, if you look at the Pacific Ocean, which is the largest ocean in the world, there is a east-west oriented cloud band from all the way from the coast of Central America all the way to Indonesia. This is the rainfall in millimeters per day, and so this east-west oriented band is what is called as the intertropical convergence zone. That is a zone where air converges from the north and the south, intertropical, and it comes here in this region, and that's what is the rain band. Now, over the ocean, this rain band moves a little, but over land it moves much more. Okay, that we saw in the animation. Now, look at India, and in the month of July, at the peak monsoon season, this east-west oriented cloud band is between Bhubaneswar and Mumbai. Okay, you don't see it every day. You have to average over many days to see this kind of picture. So, the east-west oriented band which comes over India in summer, but in winter it is to the south of India, and it remains there in winter and comes over India in summer. Okay. And in Africa, this east-west oriented band goes up to 15 north. To the north there is the Sahara desert. So, hot dry air comes from the desert and moist air from the equator comes here, and they meet along the ITCZ. Okay. So, this is a concept of the monsoon which now is considered more relevant. Now, so what happens in monsoon is whatever evaporates both from land and ocean condenses through deep clouds, and that air which rises ultimately sinks in the southern Indian Ocean, and it forms a high there because air sinks there. So, this is how this circulation is there during the monsoon. This is India here, this is southern Indian Ocean, and the circulation is there. And the quantity which is very important to understand here is called the moist static energy. It is sum of what all of us you have heard as enthalpy, or specific heat of air times temperature. Okay. What they call sensible heat. This is the potential energy of the air, because air, as it rises under Earth's gravity, it has potential energy, and this is the latent heat, the heat that will be released when there is condensation. Now, so this is a concept of ITCZ that was proposed by David Nealon and Isaac Held about 40 years ago. And so this is a concept that air converges at the surface, rises, releases heat, and then goes out on the other side. And the amount of energy is available in this column is what drives the monsoon circulation. In this column, solar energy comes on the top, that's Ft, and heat is radiated by the ground, that's Fb, and so the total amount of energy available will be Ft minus Fb, that is the net radiation at the top of the atmosphere, which we discussed earlier when we looked at the global mean temperature. Same idea can be adopted for local conditions. Now, we can integrate this equation of energy conservation from surface top of the atmosphere. This is the vertical velocity, this is the vertical gradient of moist static energy, this is pressure which is integrated vertically, this is the flux at the bottom, flux at the top. Okay. You can also write the moisture conservation equation, how moisture is conserved as vapor condenses into rain and rain falls down. That is integral again, omega the vertical velocity, q the specific humidity, and this integral gives you evaporation minus precipitation. Okay. These are the two main equations which control the monsoon. Okay. So, important quantities are evaporation, precipitation, and the moist static energy. Now, if you simplify the equation by making some assumption about the vertical velocity profile, you get a very neat simple equation which says that rainfall minus evaporation is equal to total water vapor in a column. You integrate the water vapor on the surface of the top of the atmosphere. When you integrate, you will get water vapor in kg per square meter. Okay. That is called column water vapor. And this is the net radiation at the top of the atmosphere, which we have discussed earlier, which you can obtain from satellite data. C is a quantity which is a measure of the vertical profile of temperature and moisture. We call it the stability term that controls how far the air can rise, and this is again the total water vapor. So, we have a simple equation which connects rainfall, evaporation, the total water vapor, and the total energy available. So, very important part about this concept is, if the total energy available is not positive, then P minus E is negative. It means that area is not a source of moisture, but a sink of moisture like Sahara. Okay. So, for you to have monsoon rainfall in the summer season, Q net must be positive. We will show that in the next few slides. Now, if you split the term Q net into incoming radiation S, solar radiation, which we know changes when you go back to millions of years ago, and this is the absorbed part 1 minus albedo. All of you know about albedo. Albedo is affected by scattering and absorbing aerosols, you know that. It is affected by clouds, we know that also. And we also know that clouds affect the outgoing long radiation. Clouds under clear skies, Olar is also affected by water vapor and carbon dioxide. So, you see clearly in the numerator, all these terms are affected by the greenhouse effect of water vapor and carbon dioxide, the greenhouse effect of clouds, effect of clouds on albedo, effect of aerosols on albedo, and the incoming radiation. All these things we have discussed earlier under climate change discussion, all these will affect monsoon rainfall. In the denominator are terms which are controlled by the vertical profile of temperature and humidity. Okay? And the most important term here is total water vapor in kg per square meter. If you want to see the derivation, you can look at my paper published around 23 years ago in Current Science, available easily. You can download it. Okay. This simple model reproduces the seasonal cycle of rainfall over India, South America, North Africa and South Africa. Okay? And you can see that seasonal cycle is different in South Africa and South America in comparison to India and North Africa, because the QNet, the incoming radiation, has a different cycle in South America compared to India. Okay? So this model is useful, but remember, it's a diagnostic model. This model cannot predict what will be the rainfall next month or next year. It will tell you what will be the rainfall if you know the total amount of water vapor, QNet and other things. Okay? So it's a model useful to understand the monsoon, not predict the monsoon. Now this model will tell you why in Africa the rainfall does not extend beyond 50 north. In India, rainfall goes up to 25 north, all the way to Punjab and Haryana in India. But in Africa, it is restricted to around 50 north, because in Africa there is a large desert called the Sahara, whose albedo is so high that QNet at the top of the atmosphere is negative. Okay? Once QNet is negative, we saw from that equation that QNet is negative, then rainfall cannot exceed evaporation. Okay? So rainfall is very low and evaporation is one which will dominate the conditions. Okay? This is shown clearly from this series satellite data, June, July, August average QNet at the top of the atmosphere. You see that most of Sahara, it is either slightly positive or negative. Okay? So it cannot have very large rainfall. If QNet is small or negative, cannot have much rainfall. And the same latitude to come over India, we have around 40 to 50 watts per meter squared of net incoming radiation. Okay? This is what makes India have a good monsoon. At the same latitude in Africa, there is no monsoon. So remember, very important role played by QNet, which is governed by albedo of this surface. If India were to become a desert like Sahara, there will be no monsoon. Okay? So you have to keep that in mind when we discuss the impact of climate change on monsoon. Remember that in Africa, the highest rainfall occurs around 10 north, where QNet is very high. Okay? This is the reason where there is a lot of rainfall. Now, to make this point even more clear, I am showing you QNet again and highlighting the small positive and high negative values, and showing the contours of rainfall in millimeters per day in July 1987. Okay? And you see clearly all the contours of rainfall 2 millimeters and above are in regions where QNet is positive, not negative. Here QNet is negative, here is negative, no rainfall. Okay? That is the key point. And over Saudi Arabia, there is no rain because QNet is negative. This is again highlighted with one more graph here, showing more clearly the relation between QNet and rainfall. Now, climate models which simulate the monsoon rainfall, some of them do not do well. For example, if you look at UK Met Office model called HADGEM1, it has negative QNet over large portion of North Africa, more negative than this observation. So this model will do somewhat poorer than this model, the MPI, which is somewhat higher QNet than observation. It will have rainfall going further north than in the UK Met Office model. Okay? So it is very important to correctly simulate the net radiation at the top of the atmosphere for you to get the rainfall correctly. Now, rainfall depends on water vapor according to the simple model I proposed. So we plot the column mean water vapor in any location with rainfall as shown by this paper by Holloway and Nealon, you will see that when the column water vapor is 40 millimeters or 40 kg per meter squared, you will not get much rain. It has to rise sufficiently above 40 and then it rises exponentially. Okay? Keep this in mind. The relation between rainfall and water vapor is highly nonlinear, is exponential in character. So that small increase in water vapor causes a large increase in rainfall. And this partly explains why we are getting more extreme rainfall in the last few years, because due to global warming, temperature has gone up. When the temperature goes up, there is more moisture in the air. When there is more moisture, there is more rainfall, and that relationship is not linear but highly nonlinear. Okay? Keep that issue in your mind. Okay? This is shown more clearly here. We are showing relation between rainfall and water vapor from a climate model for the present climate in blue and the future climate in red. Notice that the entire curve shifts to the right due to climate change. Okay? But notice that for the same amount of water vapor, there is less rainfall in the future than in the present. So although water vapor has gone up, rainfall may not always increase because the vertical variation of temperature and humidity controls how much rainfall occurs. Okay? So that changes with global warming. Okay? So this must be kept in mind. Now here is an animation of water vapor in the month of September in 2020, and it shows you that the source of water vapor for India is the southern Indian Ocean, Arabian Sea, and these are the places water vapor is there. That water vapor has been brought into India, and that occurs through the winds in the Arabian Sea, and that's what controls rainfall here. In the Pacific Ocean, you can see the ITCZ is stuck around 5 knots. It doesn't move much northward. Okay? Both in the Atlantic and the Pacific, the oceanic ITCZ is restricted, while in India, the ITCZ moves overland and also over East Asia. Okay? Now, in India, the water vapor is brought in India by the winds blowing from the Arabian Sea into India. So when you look at the correlation between rainfall over India and the water vapor around the world, you see the highest correlation is with Arabian Sea water vapor, okay, because wind is coming from there, okay, not with Bay of Bengal. Okay. There is a big difference between Bay of Bengal and India. The winds come from Arabian Sea, not from Bay of Bengal. Okay, now let me conclude this talk by saying water vapor influences monsoon in 3 ways. First, it is almost transparent to solar radiation but absorbed, emitted by the surface. So it is a very powerful trapping of heat. Then when it condenses, it releases latent heat in the atmosphere, which causes circulation. And since water vapor molecular weight is 18, air is 29, when there is water vapor, the air is lighter, it rises. So water vapor plays a very complex role in 3 different ways: through radiation, through latent release, and through buoyancy. So this is to be remembered when you try to understand impact of climate change on monsoon. We will continue the lecture in the next class.